Hi everyone, let's continue. So the set laws, that is the theorem 1.1.22 in your textbook. So first, we have the commutative law. A intersect B equals B intersect A. So actually, we can draw the Venn diagram, and this is the intersection is this piece, right? And you can see is commutative. A intersect B is the same as B intersect A. Second, A union B equals B union A, and when we draw the picture, union is this guy, right? So it's also commutative. And next, associative law. A intersect B intersect C, so we can intersect B and C first and then intersect A. Or we can intersect A and B first and then intersect the C. And actually, when we draw the picture of the Venn diagram, and you can see the intersection of all three of them is just this middle guy. Okay, and how about the union? Well, the union is, let me draw here. So the union is everything, okay, inside A or B or C. This is the union. Okay, so far so good, everybody. Okay, next, the distributive law. A intersect the B union C is the same as A intersect B, and then you compute A intersect C and then union them together. We can show this by the Venn diagram. Let me see. Do we have more space down here? Okay, yes. So here, let's draw it. So we have A, B, and C. So first here we want to union B or C. So B or C is, so B is here, A is here, C. So B or C is right there, right? And we want to intersect the A. Well, when we intersect the A, this is what we get. Okay, and on the right hand side, we want to figure out A intersect B and A intersect C. So let's draw the picture again here. So A, B, C. A intersect B is right here. A intersect C is right here. So when we take union of them, you can see those two regions actually are the same. So now we can verify they're actually equal. On the other side, if we have B intersect C, okay, let's figure it out. So A, B, C. B intersect C is right here. And then we want to union A. Oh, this is what we get. On the other side, so A, B, and C. A union B is right here. And A union C is right here. And then when you're looking for the common region, the common region is also this piece. Okay, can you see it from the picture? So we can show them equal through the Venn diagram. And next, we have the identity law. A union the empty set is A. Well, when you union the empty set, you actually add nothing to the set. The empty set is empty. So that's why you still have the set A. And A intersect the universal set is A. Because intersect the universal set, you're looking for the common region, but A is a subset of U. So when you take the common intersection, you just get the set A. Next, we have the complement law. A union A complements is the universal set, right? This is by definition because you have the universal set and then the set A, and then the complement is the set U minus A. So any elements is either in A or not in A. Then if it's not in A, then it is in its complement. A intersect A complement is empty. Yeah, because complement, they don't have common elements. So that's why the intersection is empty. If two sets, A and B, if their intersection is empty, we call those two sets are disjoint. Okay, so we will have the definition later, but I want to talk about that now. Okay, so if two sets the intersection is empty, it means they are disjoint. Okay, idempotent law. A union A is A intersect A is A. Okay, so then we have the bound law. A intersect the empty set is the empty set. A union the universal set is the universal set. And then we have the absorption law. A union A intersect B. Well, do you see A intersect B is a subset of A? So when you take the union, well, the biggest set just dominates, right? That's why you get the set A. And if you have A intersect A union B, well, do you see A union B is bigger than A? So A is a subset of A union B, but when you take the intersection, the smaller set just left, right? It's left. So that's why you have the set A here. Okay. What I said is, remember you have big set and a smaller set. When you take intersection, then that's the small set. When you take union, that is the biggest set. Okay. And then we have the involution law. A complement is the set A. Well, it looks like negative numbers, right? Two negative make it positive. Yeah, this is analogy for that. Okay, 0-1 law. The complement of the empty set is the universal set. The complement of the universal set is the empty set. Okay. And next we have the De Morgan's law. A union B then complement equals A complement intersects B complement. Okay. So how to prove that? I'm gonna show you the Venn diagram. Okay, let me move this guy on the left so then we can have more space here. Okay, sorry. I should save more space at the beginning. I'm not sure whether you can move your picture in your notes. Okay. Yeah, I strongly hope that you can, really hope that you can take notes, because you take notes and then you can understand what you write. And when you have questions, put a question mark next to the notes, then you can ask me the questions later. Okay? Alright, so De Morgan's law. Let me okay, pick a color. Okay, first of all, A union B complements. Well, A union B complements. Oh, okay, let me see. Alright, okay, let me see. Sorry, sometimes my computer is slow. And, okay. Alright, so we have, okay, A union B and then complement. So A and B, when we take union, that's the peanut shape, right? Complement means outside of this region. Okay, so this guy is A union B complement. And then, what is A complement? Intersect B complement. Well, A complement is outside of A, right? This guy. And B complement is outside of B. Well, but when you take intersection, well, that is the common region. Well, you can see the common region is just this guy, right? That's why they are equal. And similarly, we can prove the A intersect B complement equals A complement union B complement. Do I have enough space here? I don't. Let me move it up. Okay, let me show it here. So let me show it here. So A intersect B complement. A intersect B is the middle region, right? Complement is everything outside of it. Okay, and then A complement union B complement. A and B, A complement is outside of this A, and B complement is outside of B. And when we take union is any region that is shaded. Then you can see they are actually equal. Okay. So here, I want to tell you a shortcut how to memorize this. Okay. So, and this is just a shortcut. It has no it's not like a math rule. It's just some way that I help me to memorize this formula. Okay, so you see this parentheses, right? So the complements is really like the negative, right? So when you want to break the parentheses, you're really like distributing the negative, right? So how do I do is let me put this guy here. So this guy is like, we distribute the complements. So it's like A complement, and you put the complement on the union, and B complement. Actually, there's no symbol like this. This is just a quick way help us to memorize. Okay, so do you remember negative sign? What does negative sign do to the inequality? It flip it, right? So that's why it was union, but the complement flip it. Now it become intersection. So you see, we get this guy here. But this is just a quick way to teach you how to memorize this formula. Okay, the complements really act like the negative sign. So remember, two negative numbers make it positive, and the negative number the negative, when you multiply or divide by a negative number, it flips the inequality, right? That's why this case, when you try to distribute the complements, it flip your union to intersection, and it also flip your intersection to union. So that's why down here, so when you try to distribute the complement, so what happened to the intersection? We flip it, it become union. And you can see we get this guy. Okay, so this is just a quick way to help you to memorize the formula. And so you only do this in your scratch paper, okay? Because this bar on a union never exists. This is just a quick way I invented to help us to memorize. Okay, so that's why I'm gonna erase it here. Because I don't want you to say, oh, Suki put down something does not exist. Okay, so right, for example, I just want to show you how useful this trick is. If I give you, okay, A intersect B, complement, what is this guy? Well, you try to, so I put quotation mark here. Okay, you try to distribute it, and then this, and then this, right? You try to distribute the complements, and then A complement stay there. Well, you remember the complement flipped the union and intersection? It was intersection, now it became union, and B complement is B. So that's why you get this guy very quickly without going over the Venn diagram. Okay, so I put quotation mark here because this is just a way help us to memorize it, but it's not a correct set notation. There's no set notation like this guy. No. Okay? So be careful with that. Yeah, I want to emphasize a lot here. Yes. Because this is something special. I make it up, just help us to memorize. Okay, next, given a collection of sets A1, A2, A3, ... A sub n, the intersection of this collection of sets is, we have the notation. Now we have the I goes from 1 to n of the AI. So this means we have A1 intersect A2 intersect ... intersect A n. Okay, union with the U, we have the index I from 1 to n. So this is the same as A1 union A2 union ... union A sub n. Okay, and then sets X and Y are disjoint if X intersects Y is empty. Well, we just talked about this, right? A intersects A complement is empty. So A and A complements are disjoint. So this is the definition of disjoint. And then a collection of sets S is pairized disjoint if whenever X, Y are distinct sets in this collection S, then X and Y are disjoint. So pairwise, if we pick any pair, two sets from this collection, they are disjoint. Okay, next, partition of sets. If X is an empty set, then a partition of set X is a collection of disjoint sets whose union is the set X. If X is a non-empty set, and if S is a partition of X, then every element of X belongs to exactly one element of the partition. Okay, so for example, we can have X to be the set of the number 1, 2, 3, 4, 5, 6, 7, 8. And we can let the partition, so we can have a lot of partition, right? We can have the partition, just group the one element here and group this together and group the rest together. So we can have a lot of partitions, given the set X. So let's consider the partition, 1 by itself. And we have the 2, 3, 4 together. We have the 5, 6 together, and 7 together by itself, and 8 by itself. So this is a partition. And so here S is a partition of X. So it's just like the way how you group the elements in X. So in this case, we group 1, we group 2, 3, 4, we group 5 and 6 and 7 by itself, 8 by itself. So this is the way we group them. And you can see each element is in exactly one set of the partition X. Okay? All right. And yes, so each element in the set X belongs to exactly one element of the partition. So each element in the partition is a set. So that's why it makes sense to talk about elements belongs to the set. Because in this case, the set is the element of the partition. Yeah, remember we can have sets of sets. Okay, and what is the cardinality of S, the partition? How many elements are there? 1, 2, 3, 4, 5. So the cardinality of the partition is 5. So for sure there are other partitions, right? You can group one by itself and then group the rest together, and in this case the cardinality of the partition is 2. Or you can just group just each element by itself, and then in this case the cardinality of the partition is 8. Okay. Next topic, the Cartesian product. So the Cartesian product of sets A and B is the set of all distinct order pairs AB, where A is in, well, small a is in the set A and small b is in the set B. For example, the 1, 2 Cartesian product with the set A, B, C. So let's call this is X. Okay, let's call this is Y. Okay, so in this case, let's see, what is X cross Y? Well, this is the set of the what are the elements? So here we're gonna use the order pair notation. Okay, so this is the order pair. A, B, right? Where A is in the set A and B is in the set B. So just distinguish. This is order pair. And when we use the braces, this is a set. And there's no order in the set. So AB and BA, they're the same sets. While order pair, AB and BA, they're different, they're different points. They're different objects. Okay? Alright, so x cross y is, so we pick one element from x, so that's 1, and one element from y, it could be a, and then we can have 1b, 1c, and we can pick the 2a, 2b, and 2c. So how many elements are there? And then you can see here the cardinality of x and y equals, okay, so remember you want to pick one element from the set x. So there are how many choices? There are 2 choices, right? And you want to pick one element from the set y. How many choices? 3. So that's why in our case is 2 times 3, which is 6. So we have 6 elements. Next, we can find the other Cartesian products. We can talk about x, y Cartesian products with x. Well, this is gonna be A1, A2, and then B1, B2, and C1, C2. Okay, so you can see the cardinality of y cross x equals the number of elements in y times the number of elements in x. This is 3 times 2 is also 6. And we can also talk about x cross x. Oops, sorry. That equals, so 1, 2 cross 1, 2, well, it's 1, 1, 1, 2, 2, 1, 2, 2. Okay, so in this case, what's the cardinality of x cross x? Well, that is x, the cardinality of x times cardinality of x, which is 2 times 2, which is 4. Next, we have y, Cartesian products with the y. Well, a, b, c. Okay, so we have a, b, and a, c. We have b, a, b, 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 c, and we have c, a, c, b, and c, c. So here you can see in this case, the cardinality is y times y, so that is 3 times 3, which is 9. Okay, so remember in general, for any two set x and y, cardinality of the Cartesian products is the cardinality of set x times the cardinality of the set y. Okay, so please denote. Here you can see a cross b is different than b cross a. So if we're talking about the set operation, so the set operation, we talk about union and intersections. Union and intersection, they are commutative. So here the Cartesian product is a set operation and is not commutative. Okay, unlike intersection and union, we call A intersect B equals B intersect A union B equals B union A, but Cartesian products is not commutative. Okay, next, the Cartesian product of sets need not be limited to just 2 sets. The Cartesian product of n sets is called an n tuple. So here we have the n tuple. The notation, this guy looks like a pie, right? This guy looks like a pie, and your index eye goes from 1 to n. Okay, so this is the notation for Cartesian products. And that's it for today. We will continue in our next class. Have a nice day. Bye.